No. Alright, so in addition to the terminating event having to be defined, we also have to define the initiating event. In other words, what starts the time clock for your the timed event. And that's often a critical element that's somewhat overlooked. For example, here in the leukemia data, it's time from diagnosis to death. And so you have to make sure that you understand what the elements of the diagnostic process are, and making sure that the patients are uniformly diagnosed with the same methodology, so that we're all talking about the same time to event for all the patients. And the idea is that these are cohort studies, so patients are followed periodically in a prospective manner from the initiating event to the terminating event, or until the end of the study. So censoring, like I said, is this issue where you're following a group of subjects over time, and then you don't want to wait until everyone has suffered the event of interest, because that could take 20 or 30 years. So you decide to analyze the data before everyone has suffered the event of interest. And so for those patients that haven't suffered the event, we call them censored. And so the patient could be alive after 2 years of follow-up, and all you know is the patient is still alive and has been alive for 2 years. So you don't know their actual time to death. So what you have is the lower limit, so the patient that was alive for 2 years could end up dying at, say, 25 months, or could die 20 years later. You just don't know. All you know is that they were alive for 2 years. The basic data you have are the time to the event or the end of the study, this time variable, and an indicator as to whether or not the event occurred. For example, in the leukemia data, you have survival time, and then you have vital stats. It's a live dead indicator. And those two pieces of information are the key pieces of information that you need to analyze survival time data. If you just look at the survival time without looking to see whether the patient was alive at the end of the study, your predictions are not going to be as accurate as if they were made using the information about whether patients were alive or dead, especially if there's a high proportion of patients that are censored. For example, I'm analyzing a data set now in testicular cancer where 90% of the patients are censored. It's a big data set, so we have enough deaths to analyze, but it's censoring there. If you ignore it, you get completely distorted answers. So we are assuming that the censoring is non-informative, which is just a fancy way of saying that the patients who are censored have the same underlying survival experience of those patients that aren't censored. In other words, it's random censoring. All right, so one of the things that is particularly emphasized in survival data time analysis is the survival function, which is this function that describes the proportion of patients surviving beyond some given time. So we have some notation that we like to use. So let's say capital T is the survival time for an individual patient, what we like to call a random variable. And then little t is a specific point in time. So we have this survival function called, funnily enough, S of t. And so you say that, for example, S of 5 would be probably surviving past 5 years. So it's the probability that the patient survival time exceeds the specific time point of interest, for example, 5 years. All right, so you might think that this is totally new, but it's not really. Most of us are familiar with the histogram, which is just a data display, is a bar graph with the density of the data. In other words, along the x-axis are displayed the possible values of the variable, and the range of values are divided up into intervals, and the number of patients in each, or subjects in each interval that have that values within that interval is graphically displayed by bars. So that's a histogram. And that's a graphical illustration of what we call the density function. And so if you just add up those bars from left to right. In other words, you're integrating this function. You get something called the cumulative histogram, or what we call the distribution function. And if you just split that over, so instead of starting at 0 and going all the way up to the maximum number of subjects, you start at the maximum and go down to 0. So you're just taking the complement of these bar heights. That's the survival function. That's all it is. It's just basically a mathematical manipulation of what we're commonly seeing when we see the histogram. So we usually present it as a step function with the jumps determined not by preset intervals, but the jumps occur at depth times. We'll see that more clearly later. So the survival function, again, is a commonly used distributional function in statistics, but it becomes of paramount importance for survival analysis, partly because clinicians like it, they can understand it readily, and because we have nice statistical methods to analyze it. So the common method for estimating survival function is called the Kaplan-Meier product limit estimate. Kaplan-Meier, they're statisticians who actually, it's an interesting story, they independently submitted papers to the Journal of the American Statistical Association, and the referee said, well, these are very similar, so they asked them to work together to create a joint paper, and this was back in the 50s. But if you read it, it actually reads very disjointed. It's a very complete paper, but it has a lot of interesting things in it. But it's just a medical story. So we have this Kaplan-Meier estimate, and the survival function is the probability of the subject surviving beyond some given time t for every time t from 0 to however long you want to go out. And so the idea here is that the probability of survival is conditional. In order to get to t, you have to survive up to t. So say t is 5 years. In order to get to 5 years, you have to survive the first year. Then you have to survive the second year. Then you have to survive the third year, and so on. So there's this notion of conditionality. And then one more aspect that we like to emphasize in statistics is that we don't know the true survival function. We have a set of data, and we're trying to estimate the truth from that data set. So all we have is an estimate of the truth, not the truth itself. All right, so here's a little mathematics, but it's pretty straightforward. So what we do is we take the survival times, we rank order them from smallest to largest. Then we look at each death time. And we look to see how many patients are alive at that death time, how many patients die at that death time. Take that difference, which is the number surviving, number of patients or subjects not dying, N minus D, and divide it by the number at risk. So that's a survival probability. Then we multiply these up at each of the death times as if they were independent probabilities, as you would do. So the idea is you start at the beginning, the first death time, you do this calculation, and you do it successfully thereafter, building up your survival estimates. So we have D is the number of deaths, N is the number of subjects, N minus D is the number of survivors. And you can see that this function is also equal to 1 minus D over N. And that will come up in a minute. So here's a little toy example. It's a real example from Andy Anderson a long time ago. Leukemia example, acute leukemia. A clinical trial run many years ago. A small clinical trial. And these data are in weeks. We have 21 patients in each of two groups. One with an active treatment and one with placebo. And the data are sorted. You see we have ties at some of the death times. And these plus signs indicate censored observations. So at 6 weeks, we have 3 people that died and 1 patient that's censored. And then so on. So we have, going out here, the last 5 observations are all censored. And you notice in the placebo group, there is no censoring. You see we have some ties here as well. At 8 weeks, there are 4 patients that died. So if we want to calculate the survival function, we need the basic elements. So we rank order the death times, from smallest to largest. These are the unique death times. There are going to be some ties for some of these. For like 6 weeks, there are 3 patients that die. Out of the 21 that were at risk. And as you go down, you lose patients because they either died or they were censored. So you start with 21, and at various death times, you have different amounts of numbers of patients who are at risk. So to do the calculation, at the first death time, we have 1 minus the number dying, which is 3, over the number alive, which is 21. So that probability is 0.86. We do the same thing for the second death time and the third death time. And then you multiply these together sequentially to get each of the successive survival probabilities. So it starts at 86% and it goes down to 81, 75, 69, down to 45%. Now we can graphically display this by just showing the survival probabilities over time as a step function. It starts at 100%, then it drops down in each of the unique death times. So there's a drop at 6 weeks, and because there were tied death times, it's a fairly big drop. And then it goes down, as you can indicate there. This is, like I said, in weeks, 30 weeks. So here's the placebo group. It's the same deal. There are more unique survival times, but the same calculations apply. And this starts at 90 and it goes all the way down to 0. The last patient died. You notice in the active treatment group, the last patient didn't, the last 5 observations were all censored, so the survival function just hangs out here. It doesn't go down to 0, because that only happens when the last patient dies. Alright, so see here is the step function, the Kaplan-Meier estimate of the survival function for the placebo group. It starts at 100%, and it goes down to 0% at about 23 weeks. Alright, so in survival time data, the median is much more important than the mean, because we can estimate the median very easily with the Kaplan-Meier curve, just by noting where it crosses 50%. So the median is the value defined by having half the values above it, half below it. So you rank order the values, and it's the value in the middle. That's the mean. So it's easily estimated with right-centered data, as long as the survival curve crosses 50%. If it doesn't, then you can't estimate the median. All you can say is that the median exceeds the range of the observed data. And like I said, the median is a good estimate, it's a robust estimate of survival time. Most survival time data are skewed. If the leukemia data are highly skewed, if you look at it, the density function is very exponential, with lots of short death times and not, very few really long survival times. And it happens with censoring, you can't estimate the mean reliably. The more censoring you have, the more biased the mean estimate is. And this is the mean computed from the Kaplan-Meier curve, not the mean computed by adding up the survival times and divided by the number of survival times, because that estimate of the mean is totally biased. So you can actually get one that's less biased by using the area under the Kaplan-Meier curve, which is another way of computing an average. But again, it's biased because of the censoring. Because basically, you can't estimate the right tail of the distribution when you have censored survival times. Very reliable. If you have lots of censoring, you can't estimate it. So the median is the point at which the survival curve crosses 50%. So for these data, it's 8 weeks. Alright, so the next question we have is, how do you compare survival time distributions? What statistical methodology can you use to say whether 2 groups, for example, the 2 groups in this data set, active treatment and placebo, whether they have the same survival experience? So, we have what we call our null hypothesis, which is just that the 2 survival distributions are the same. It's a very general hypothesis. We want to use methods that can address this hypothesis. The most common method is the Cox proportional hazard regression model. And we use the hazard ratio, which we're going to define later here in a minute, to quantify the association between variables and the survival time. All right. So now the fun starts. So we have this thing we call the hazard function, which is just the limiting probability of dying at a certain point in time, given that you survived up to that time. So the shorthand is the instantaneous death rate among the survivors. Right? So it's if you think about it, you're following patients over time, and say 2 years, you want to say, what's the probability that patient's going to die right then? Like that day. And you do that for every successive time. So what's the probability that the patient that's made it out this far is going to die right now? That's the hazard function. It has this fancy mathematical definition. But it's just a limiting probability. It's a limiting conditional probability, if you will. So there's a nice paper written by myself. And it's in clinical cancer research. It talks about the hazard function if you want to become more familiar with it. Actually, my better work. It's actually readable. The hazard function is connected to the survival function by a sign, a derivative, and a log. So you take the log of the survival function, you take its first derivative, and you negate that, and you get the hazard function. So the main story here is that you can't tell what the hazard function is by looking at the survival function because our minds cannot mathematically manipulate data that way. You can look at it, and you might be able to tell what the slope is, but you really have difficulty taking a log mentally. So it's just very problematic to do it mentally, looking at one function and trying to figure out what the other function is, but they are mathematically linked in this way. So if you know the survival function for a data set, you can calculate the hazard function. So the thing about rate functions, and this hazard function is a rate, it's an instantaneous rate, is that they're highly variable, much more so than the survival function, which are probabilities. So they're not nearly as variable as rates are. So a rate is like the number of deaths per week, as opposed to probability. So we have these methods to smooth them. And this tells you, this is useful to know what the hazard function is because it tells you what the underlying death process is. Okay, so in R we have a library called NewHaz for estimating the hazard function. And it works just like smoothing histograms, so you saw that histogram. So the idea is that you just you smooth over that. So you have all these points in time and you just squish all that stuff together. And we have these fancy methods to do that squishing for you. So here's the leukemia data. This is the Kaplan-Meier curve for the leukemia training data. So it has 26% of the 191 observations are right censored. The median is 1.4 years. And the data are consistent with the median anywhere between 1 and 2 years. So then we're estimating the median. We don't know the true value. We're saying the true value probably lies between 1 and 2 years. And you can see it starts at 100% and then drops precipitously. So it's 56% in 1 year, and then 35% in 3 years, and then it tails off and starts plateauing out as you get past 5 years. And you can see here there's a lot of censoring above 5 years. All those tick marks on the Kaplan-Meier curve are censored observations. There's not much censoring early on. All the censoring is mostly happening later on. So here's the hazard function for these data, estimated using our NewHaz library in R. So you can see what's happening with these data. Early on, there's a very high hazard rate, and then it drops like a rock. In 5 years, it's very low. So after 5 years, the hazard rate for dying is very low. but it's very high early on. It's like when you look at the survival time distribution, you can actually see that it's highly, highly skewed. Lots of short times and not very long times. Okay, so the model that's by far the most widely used model for analyzing survival data, especially in the medical literature, is what they call the Cox proportional hazard regression model. It was developed in the 70s by D.R. Cox, and it has this clever functionality based on the hazard function. So we have the hazard as a function of time and covariate values. So it's written so that you have this baseline hazard that you do not have to estimate to compute the regression model. It's a nuisance parameter. And so if you take the log of both sides of this, you get basically a linear type function. So it's linear in the log hazard scale. So it's like the log is the baseline hazard plus beta x. So it's like a plus bx, like the line. So we call this a generalized linear model. And you can see just with a little algebra, for a single binary covariate, it's coded 0, 1, usually 0 for absence and 1 for presence. For the absence group, we have just the baseline hazard. And then for the present group, we have just the baseline hazard multiplied by the inner log of beta, e to the beta. When we take the ratio of those two functions, we just get e to the beta. So this is what this model is assuming that these hazard functions are in constant ratio. In other words, that they're proportional. This is a very restrictive assumption. There's a lot of data sets, including the leukemia data set. This is not full for every covariate. And it can interfere with your predictions. You have to be careful about it, assuming that the covariance effects are constant over time. All right, so for our little example, we get a hazard ratio of 0.2. Saying that the hazard rate in the treated group is 1/5 that in the placebo group. And it's highly statistical. So the hazard ratio ranges from 0 to infinity. With values less than 1, meaning if you code it as we usually do, where you have 1 is the adequate treatment, then less than 1 means the treatment works or it's protective and prolonged survival. We often use the log hazard ratio because it's symmetric. It ranges from minus infinity to positive infinity. And the hazard ratio of 2 is 0.69, and 0.5, which is 1/2, is minus 0.69. So there's a symmetry in terms of the effects of a covariate, whether it's doubling the hazard rate or halving the hazard rate, which is really the same effect. On the log scale, you get the same magnitude, but if you think about it in terms of the hazard ratio of 2 and the hazard ratio of 1/2, it's not necessarily conveying that that's the same magnitude of effect. So these pictures are of exponential survival curves, and they're satisfied with the proportional hazard assumption, and they have varying degrees of hazard ratios associated with them. So a hazard ratio of 0.8 is fairly denoting curves which are fairly close together. So there's a relatively small difference in the survival curves. And hazard ratio of 2/3 is a little more dramatic. A hazard ratio of 1/2, again, is a doubling or a halving of the hazard rate. Not that dramatic. And cutting it in thirds, you still see this sort of kind of relation. So you see, it takes a bit of getting used to what the relationship between the hazard ratio and the separation of the survival curves is. All right. So what do we do with numeric covariates? So if you write censoring, it inhibits our usual methods for analyzing data. So ordinarily with numeric covariates, we plot the outcome against the covariate and do a scatter plot. If we just have some kind of plotting age against albumin, we just want to know whether looks like albumin, whether it increases or decreases with age. So you just do a scatter plot, and you can do a correlation coefficient. But with such data, you can't use those methods because of the censoring. So we have a couple options. One is to do residuals. And residuals in statistics is just the difference between the observed values and the predicted values from the regression model. We call those residuals because we like to have these nice reserved words that mean special things to statisticians. It makes us feel special. So we have residual analysis that you can use. Today, for the sake of time, we're not going to talk about residual analysis, but there are lots of textbooks and articles online. So there's an entry in Wikipedia about taxonomical residuals. Particular martingale residuals would be what we'd be looking for. And we're going to talk about another approach called scatter plot smoothing, which is a way to graphically show how the survival changes with the covariate values. Based on the method I'm going to show is based on the Kaplan-Meier approach. It's like having a moving average. But we know what a moving average is. It's like placing a window over the data, calculating an average in a window. So it's a local average, and then you move that window from left to right across the data value. And this is work from Adrian Bowman. And again, all the stuff that I'm talking about here is basically last century methodology. So the idea, the challenge is to move it forward using these, working off of what was done last century. And this stuff is for low dimensions with 200 protein expression values. Some of these methods have to be adapted and tweaked because they're mainly working for low dimensions where you have maybe a dozen covariates, and they don't work that well when you have 200. And they certainly don't work in microarrays, which I have more experience with. When you have 10,000 variables, you have to do a fair amount of adapting the methodology for the high dimensional space. I'm not going to talk about given the time constraints. So here's the age diagnosis for the patients in the leukemia training gate. So it's fairly a little pushed to the right. It's not completely symmetric. So there's a left tail. There's an outlier. There would be 1 or 2 kids in the data set. Mostly they're young. I consider them young because the median's around 60. All right. So here we can have Kaplan-Meier curves for 3 groups based on age. You see the young patients do relatively well. They have a median survival of around, well, it's not actually even reaching the data. So it's going to be somewhere around here, maybe 8 years. But we can't estimate it because the survival curve doesn't cross 50%. For the middle group, the median is about, it's less than 2 years, about 1.2 years. And then for the older group, it's less than a year. You can see that for the older patients, they do much less well. So, rather than categorizing the patients based on age, we want a more direct assessment of how survival varies with age. When you do a scatter plot, and the thing about when you do a scatter plot of system data is that you want to make a distinction between the patients that are alive, these circles, and the patients that have died. Because for the dead patients, you know their survival times. For the patients that are alive at the time of the analysis, all you have is a lower limit. So you can't really visually assess how the average survival time changes with age. So what we do is we just have a moving average type estimator, and it computes the median within a window, and it moves that window across the age distribution. So you can see the median age for the young people is relatively long, in 8 years. And it drops down, so it's around 2 years at age 40, around 1 year at age 60, and 80. One thing you can see is that in each of these ages, there's quite a bit of variability in the survival times. So there's clearly a relationship between age and survival, with the survival getting lower as age gets higher, but there's still a lot of unexplained variation, which is recognized as the variability in each of these ages in the survival time. All right, so here is the full-blown Cox proportional hazard regression model showing the multiple covariates. It has the same basic structure, the baseline hazard, and then e to the sum of the beta x's. That's a typical statistical regression formulation. And again, if you take the log of both sides, you see it has the basic structure of like a linear regression model, a multiple linear regression model. So if you think about a single numeric covariant, let's call it having a value A and then a value B. So if it has value A, then you just clearly have the baseline times b to the A beta, and the B's baseline times b to the B beta. Then you take here, we're going to get a little more clever and talk about the log ratio. So the difference in the logs right over the log of the ratio. It's the difference in the logs. It's just beta times the difference in the covariant values. So if you're talking about a difference in age, you take from 20 to 30 years, the difference is 10 years, so it's 10 times beta, and that's the effective age. Alright. So the rest of this has to do with analyzing the leukemia training data. So you can look at the cytogenetics variable, which is a categorical variable with lots of categories, and you can separate those categories into groups that have similar survivals, and they actually span the relative range of survival. So you have some of the cytogenetics have relatively good survival, and some of those categories have relatively poor survival. So cytogenetics is clearly related to survival. And chemotherapy, obviously, when looking at the data, some of the chemotherapies do better than some of the other chemotherapies, which may be due to the selection process and selecting who gets treated, or actually may be the treatment type itself. And then we have some numerical variants. For example, there's albumin. Again, it has a roughly bell-shaped distribution. It has an outlier on the low side. And it has a relationship with survival. Unlike age, as albumin increases, survival gets better. And you see the survival median changes from less than 1 at low albumin. At middle albumin, it's about 2. At high albumin, it's about 4. So it's not quite as dramatic a change as we saw with age, but still there's an obvious relationship between survival and the albumin. And hemoglobin is more or less symmetric. It has an outlier on the high side. And one of the things you have to be careful with the Cox model, if you have a death that's an outlier on the high side, that can have a very influential effect on the covariate value, the regression coefficient estimates, and hence your predictions could be off. So you have to be careful when you have deaths that are outliers on the high side, that they can exert too much influence, and you want to be careful about that. So you can look for identify the outliers, and then see whether they're having an influential effect. And you can easily do that by running the model with and without the outlier and see if the regression coefficients change much. And then the remedial methods that you can use to reduce the effect of the variation, or you can use methods of estimation or resistance for that sort of influence. Alright, so here's the median survival as a function of hemoglobin, and it, just like albumin, the median survival increases as the hemoglobin increases. So the patients with higher hemoglobin do better. It has basically the same kind of shape as albumin. It's interesting because hemoglobin and albumin are not correlated. They're not conveying the same information. They just happen to have the same sort of relationship with survival. Alright, so here's a typical way we present the Cox regression analysis. So these are just some of the clinical variables included in the Cox model. So we have age, we have hazard ratio for a 40-year increase in age. And I picked 40 because it's basically the interdecile range, so it's a difference in age between the 10th percentile and the 90th percentile. And when you're presenting hazard ratios for different kinds of variables, it helps to put, you want to try to put the hazard ratio for numerical variate, which when most of the software, when it prints out the hazard ratio for numerical variate, it's going to give you the beta value for a 1 unit increase in the covariate. So if you have the covariate that ranges like age does from 20 to 70, that means one thing. But if you have a variable, so like a biomarker that varies on from 1 to 3, a 1 unit increase is a pretty hefty increase. So it means the meaning of the hazard ratio associated with a 1 unit increase depends on what the range of the covariate values is. And one way to help deal with that is to present your hazard ratios for something like the interdecile range with a pretty hefty difference in the covariate values, and that kind of puts it on the same footing as we get for like the dichotomous variable like chemotherapy. So we see a 40-year increase in age, which results in a tripling of the hazard rate. This is adjusted for all the other things in the model. And the chemotherapy, the favorable chemotherapy, cuts the hazard a third. And then there's cytogenetics, looking at two groups here. One of the groups has twice the hazard rate of the other group. And albumin, 2 unit increase, and cuts the hazard in half. And hemoglobin, 4 unit increase, cuts it about in half. So we have this model with these 5 covariates. So we want to say, well, how well does this predict survival? And we use the concordance index, which is based on a rate correlation between the predictions and the observed survival times. So if you look at age alone, it has a concordance index in the training data, and this is just using the training data, not being sensitive to overfitting, there's no cross-validation, no bootstrapping, just using all the data. So of course, if 5 is high, it's not at all attempting to be an unbiased estimator. It makes sense. I'm just using it to demonstrate the predictive strength of these various models. So age by itself is 63. Now for the concordance index, the value of 0.5 is for random variability where there's no relationship between the predictions and the observed values. So you're going from 0.5 to 0.63. Then you add the first 3 variables, age, chemotherapy, and cytogenetics, and you increase that to 0.68. You add albumin and hemoglobin to that, so you have all 5 variables, and you increase it to 0.72. And then I looked at the best 10 protein expression values just by ranking them by their individual concordance indexes with survival times. Because you can just compute the concordance index between marker and survival. You can do that for all 200 of them and just rank them and just pick the top 10. And you can see that when you do this kind of mindless way, you don't increase the predictive accuracy that much. That's why you have to be fairly clever about how you choose the features. And this is, why the challenge is a challenge, because it's a really hard problem. So we increase the predictive accuracy above what you can get with the clinical variables alone, which is what your challenge is, because the clinical covariates by themselves do predict survival to a certain extent. But you want to do better than that using the protein expression. Okay. So here is the distribution of the linear predictor is the part of the model which is the sum of the x betas, part that's in the exponent when you write the model out. So for each case, you just take the covariate values and multiply them by the respective regression coefficients. And so you get these linear predictors. So these are, in a sense, proportional to the actual predictions. And for these measures of predictive accuracy, you don't actually need the predictions. You just need something that's proportional to the predictions. So you can start with the linear predictors. You can see that this distribution isn't very informative in itself, but it's helpful to know what the shape of the distribution is. Because, say here, we're plotting the median survival is a function of these linear predictors. So the patients with really low values for the linear predictor have relatively high survival, again, relative to the other patients, not very high. And AML is a bad disease. So you can see that as the prediction, as the linear prediction increases, the median survival decreases precipitously. But you can see that the variability of each of these linear predictor values is pretty excessive. That's all the unexplained variability. That's why the C index is only 0.65 or something like that. That's what it's reflecting. It's all that unexplained variability. So we can predict survival using these same covariance to a certain degree, but not very well. So the challenge is to build using more methods of data mining that are sensitive to the right censoring to improve that prediction and get over this hump. Which is if you read the clinical literature, there are not very many clinical predictors that have high concordance indexes. Like they're in the low 70s, generally speaking. The good ones are in the low 70s. So here we just chop up the linear predictors into 5 groups, and we can see that the Kaplan-Meier curves, the ones that are predicted to have good survival, have reasonably good survival. What we really like to see is the ones that have the best survival, having survival up near 100%. Because you want the Kaplan-Meier curves to span the range, going from 100% down to 0%. So you can see that right off the bat, we're not doing real good in isolating the patients that do really, really well. And then the other thing is these curves are not all that well separated at the beginning, which is another issue in terms of being able to separate out the initial behavior. And one of the things that we stat is that the Cox model assumes that everything is constant over time. And so what we expect to see are survival curves that are well separated, they don't converge, and they don't cross. They're well separated, and they span the range of values from 100% down to 0%. So it does a reasonable job, but not directly a very good job. So the other variable that has to do with censoring in leukemia data is the remission duration variable. And it's a little trickier than death, because death, you just have a live death. With remission duration, what you have to look at are the 2 variables, relapse and death. So if you cross-tabulate those 2 variables, and this is among just the patients that had complete remission, because they're the ones that the remission duration is relevant to. It's not relevant for the patients that didn't get into complete remission. It means the cancer didn't go away, they're resistant to the therapy, and they're in a different step. So if you just look at the patients with 136 that had complete remission, at the end of the study, 31 patients out of the 136 were alive and free of relapse. That means they're still doing well. They're still in remission. We have 13 patients that died without relapsing. So they might have died from therapy, or they might have died from getting hit by a bus. But they didn't die necessarily from the cancer relapsing. Maybe there are other issues that could rise from that. There are 13 patients that have relapsed but haven't yet died, and the bulk of the patients have died after their relapse. So the idea here is that 31 patients can be considered censored with respect to remission duration. So again, you can't just look at the remission duration variable by itself. You have to look to see which patients that's an actual value and which patients that's a censored observation. So 31 out of the 136 is censored. Here's what the relapse-free survival curve looks like. In other words, the survival function for the remission duration. For the 136 patients, it's median about a year. It has the same basic shape as the overall survival function. And all all the issues that I talked about before with respect to overall survival apply to this variable. In fact, it's so similar that all the issues pretty much just translate directly to this endpoint as well. Alright, the caution about the censoring is a big deal. You have to make sure the methods that you use are sensitive to the censoring. And good luck with the challenge. Thanks again for inviting me to speak.
Okay, thank you, Dr. Hess. We're gonna first take questions from the audience here. If you're following us over the webinar, please type your questions on the questions tab, and we'll get to those afterwards. Anybody in the audience here has a question? I do have a question. You mentioned about the outliers. You said you had to be careful with them. Do you have any particular way you like handling outliers? Do you just remove the patient? Do you round that down to upper bound, as standard deviation or something like that? Or how do you have any suggestions?
So the bill is thinking you don't want to remove it, but there's no universally accepted way of handling it. Hopefully you can find some methodology that's resistant to the effects of the outlier. So there are methods that make the proximal resistant, not to use the methodology. So like ridge regression, familiar regression, like they're constructed to be less influenced by outliers. And then there are remedial things you can do, like locking them down a little bit, seeing what the effect is. So it's a lot of like a sensitivity analysis, where you do take various actions to see what the effect is. There's not like one easily applied solution to the problem, especially because you're talking about outliers in 200 space, not individual outliers. So if you think about the outliers in 200 space, just trying to identify outliers in 200 space is itself a difficult problem.
But when you say see what the effects are,
On the regression coefficient estimate, that's what's driving your prediction. So if you see a dramatic influence when you take one of the patients out, and your regression coefficients are suddenly different, and this can happen when you have a big outlier, especially if it's an outlier in more than one variable, then that can have a noticeable effect on the parameter estimates. And so then you know you need to do something, and what that is controversial. Like I said, there's no universal solution.
thank you. Sure.
So when compared with the index, so it seems we add, we continue to add more information and we get practice index values. So my question is it possible we add like more proteins here? So if we add more proteins, is it possible that it may decrease the index?
Well, generally speaking, if you add, it's not strictly speaking that you're going to get, if you just add random noise to your predictor, it's not like R square in linear regression where it just increases and increases without them up to its maximum as you add variables. And so that you have to adjust to that. It doesn't behave in exactly that same way, but just there's this general idea of avoiding overfitting. You want to avoid relying too much on issue or features of the training data that may not go to the validation data. So you have to be careful about the robustness of the model. And the other thing about the C index is it's known not to be very sensitive to incremental increases in predictive accuracy. So you get diminishing returns as you add additional predictors. It's just inherently known that it has this it's not really a ceiling effect because it will continue to increase. it doesn't increase very dramatically as you add more and more predictors.
I have a question about censoring. So, does that affect the analysis? Says some patients may get censored because they're good, so they don't come to the clinic anymore. But some people they be too ill to come to the clinic, so they get censored. Does that make a difference in the analysis?
Absolutely. If you know that you're the source of the censoring, because that's informative censoring. If you know why the patient's censored and it's related to the outcome, in other words, they are not, those patients that are censored don't have the same underlying survival experience as the uncensored subject, which is the fundamental assumption. The Kaplan-Meier method, the Cox model method, the usual method for survival data, you have to use methodology that's specific for informative censoring. We have specific classes of methodology that compete with this methodology, and there are specific kinds of informative censoring, and there are other kinds of methods for other kinds of right censoring. So it definitely matters. If it's only a small percentage, then the difference won't be very large. You use the fancier methods as opposed to the standard methods. But if that fraction of patients who get censored informatively, in other words, they're censored for reasons that's related to the outcome you're trying to measure. If that's true for more than a trivial proportion of the patients, then you have trouble.
Thank you. Any more questions from the audience? Let's go then into the webinar questions. I don't see any questions out of the webinar. So anyone, please type your questions in the questions section. I don't see any. So there are no questions from the webinar, so thank you, Dr. Hess. The last round of applause.